Hello, so good morning everyone. So I am Omkar Kokne and I would be presenting you the paper Retrospective, a CORDIC-based configurable activation function for neural network application. So the paper ID is 98 and this has been accepted in VLSI for applied and future computing. Moving towards the list of author, I am being Omkar Kokne from IIT Indore, the first author, with other authors like Gopal Rao, Salimullah, Mukul Lokhande, Adam Tayman, Akash Kumar, and Santosh Vishwakarma sir. So, before moving towards the paper, first let's understand some basics of what is a CORDIC. So, CORDIC is a algorithm which uses multiple dimensions to convert the data into uh, an operation, a function. So what it performs, that it can support trigonometric operation, it can help with hyperbolic, logarithmic, division, multiplication, and the list goes on. And not only that, but uh, its hardware architecture is also simpler. It just consists of an adder subtractor, some shifters, a small of LUTs, and some constant values, so resistors for those, and that's all. You can observe in the bottom left the equation of the CORDICs. So whatever CORDIC, you just provide a single input to one of the variables of x0, y0, or z0, and it will iteratively keep on trying to reach its what I can say selected output value, as you can see in the GIF. And how is this being selected? So based on the variables in the equation like mode m, the constant of ei, which we provide through resistors, and also a initial value of scaling of ki. So it has three coordinate modes of linear, hyperbolic, and circular, and with help of these we select which activation function or which operation we want to perform. Now, moving towards the history of CORDIC, as the paper is a retrospective, so we like the CORDIC was not invented recently. It was invented very year, like long time back. So currently we are in 2025. It was introduced in 1959, and not only that, like people are continuously working on CORDIC since then. There was also another person of John Walter, who then provided a unified CORDIC algorithm in 1971, and since then the CORDIC is used in activation functions, in hardware, and in many more aspects, and that too not only for fixed point arithmetic or so, but people are also using that for floating point, posit arithmetic, and also its implication is day by day getting diversified. Not only that, but CORDIC is also integrated in several IPs, hard IPs like AMD's Xilinx FPGA 2022-2023 IP catalog. There is a IP for CORDIC algorithm. In Intel's DSP builder of 2022, there are also CORDIC algorithms used for calculation of several operations. Same goes with microchip, HP, ST microelectronics. Not only the hardware, but few software libraries also have CORDIC in those, like MathWorks and NI. Now, why, like, okay, we studied about CORDIC, but what is the need of this diverse activation function, you would ask? So as we know, we are today using, we also want to use audio features of AI, we also want to use video feature, we also want to use its chat feature, but as if I observe it in a computer science perspective or a engineering perspective of a computer science, so I would see that every different model, every different application requires different activation function. Now, how are you going to get these activation functions? So if you are creating an AI accelerator for these, so you will also need different activation functions for different applications, and now that is where your excess area or excess power goes. This creates the dark silicon. So to solve this problem, to solve support for all these activation functions like Sigmoid, Tanh, SoftMax, Swish, SELU, GELU, and many more. So what we did a thorough analysis first. Like what are current, how many activation functions are supported in current works. So we observed that max to max 3 or 4, probably mostly it was 3. So we came up with why not to make something which will support a lot number of activation functions, not just for DNN or not just for LSTM, but for vision transformers, LSTM, RNN, DNN, and so and that too at it should be capable of diversifying at different what you can say bit precisions. So we use this CORDIC approach to create a fixed point based 8 and 16 bit arithmetic, a SIMD based work. Okay, and this design approach is based, as I said, it's using CORDIC at its base. So let's go towards the block diagram of the complete architecture of processing engine. So we name this as Nuric PE, where there is a mag block which would be performing all the mag operations of like multiply, add, accumulate. Then that accumulated value would be sent towards the activation function. Now here, based on the select AF 3-bit line, we would be selecting which activation function we want to select. Then with the help of that and providing the constants required like T and beta. So T here is approximation for the GELU part, which I showed in the equation earlier, and beta similarly for a specific activation function for the scaling. Then it would be multiplied, that scaling would be performed. Further, it would be sent towards the CORDIC hyperbolic block, and after some computations and like addition and generation for the exponent terms, those would be sent towards linear CORDIC. Now this stage would be used where you want to perform softmax, sigmoid and all, and with this it is also again sent towards the next HOA adder, which is an overestimating adder which performs a +1 operation by in its default structure without much accuracy loss. Then further moving towards the final scaling at the end of multiply if required, and then the output is directly sent through mux to the as the output of complete Nuric processing engine. Now you would think like, oh, we are using CORDIC based approach, so CORDIC could have what you can say some error in it, as it is an approximating approach, as it goes on by reducing the errors. So yes, we also did this thorough analysis at different bit precisions like 8-bit, 12-bit, 16 and 32 bits. So we also observe that the error in the values are less than 7 into 10 raised to the power 3, which is like very low, and as compared to also other what you can say work and other approximation algorithms. Not only that, but we also did this for diverse type of activation functions which we are supporting. Now the DaVinci block is just the activation function block, and the complete Nuric PE is including the Mac part in it. We have tested this on FPGA, which we observe the mean error around to be like 2.78% in the values. Then we are also using SIMD based architecture and supporting the precision of 8 or 16 bit. We also observed the less amount of LUT and flip-flop used due to the reconfigurable design, and the delay is around 2.56. Yes, we know it's a little bit more because of like having several of those block in the path if those are being computed. Also the power is required is around 30 milliwatt for the activation function part. The same was like evaluated on the ASIC level, where we observe a area of around 2k micrometers, 2000 micrometers, then delay of around 2.6 nanoseconds, and with around nearly 60 milliwatt of power consumption. which is very less resources as compared to other designs, while providing more features. Then we like move on with the complete analysis on a particular accelerator design. So we have used this vector engine based accelerator design for evaluating of the numeric PE. So what we observed that the complete numeric PE when tested on FPGA Virtus VC707, we observed its arithmetic intensity to be around 133 picojoules per operation. So we further go into depth and analyze this FPGA result on the same board for the complete vector architectural design, and we observed that at a power of 1.54 watts, we are getting GOPS of around 8.4 for GOPS per watt. So which is a good number, and it is capable of operating at a frequency of 354 megahertz. Now you would say, okay, all that's fine, but won't my accuracy get lost as I'm using an approximate? So yes, we also analyze the accuracy, where we observe like there is not much of a variation when compared to other approaches and the proposed approach. As you can see in the graph, we have not only tested for the DNNs but also for mobile VIT, ResNet, and many more. So thank you everyone for giving us a chance for the presentation, and wish you a good day.